In the long memory of the universe, most years pass quietly, but some years refuse to remain ordinary. Some years arrive like a question whispered into the darkness. 2025 is one of those years. It is the year humanity looked up and felt for the first time in a long time that something unfamiliar was looking back. Astronomers noticed it slowly, at first a new detection here, another there. Then the numbers grew. One interstellar object. Then 2. Then 5. Then 7. 7 star-born wanderers entering our solar system within the same era, a statistical anomaly so extreme that many scientists checked their software twice. Among them, one object drew more attention than all the others combined, not because it was the brightest, not because it was the closest, but because it behaved like a riddle written in the dark. 31ATLAS. When it crossed the orbit of Pluto, it was barely a footnote in the data, a dim streak, another cold visitor from deep space. But once its orbit was solved, everything changed. Its path was deeper than expected, its speed stranger, its brightness inconsistent with known comet models. Its inferred shape suggested hollow geometry, and its predicted behavior near the sun split the scientific community in half. Some said it would behave like any other comet, brighten, outgas, shed dust, move on. Others thought it might fragment. A few wondered whether it would do something no comet should do, change course. And at the center of this storm of speculation stood one voice that refused to be ignored, Avi Loeb. The night before Perihelion, the Harvard astrophysicist released a short message to the world, calm in tone, but loaded with implications. He called the coming solar encounter a stress test, a moment when the object's true nature, natural or otherwise, would reveal itself through its behavior. The message ricocheted across the scientific world in minutes. Some criticized it, some amplified it, some quietly admitted that he had a point. Because 3I et TLAS was not simply another icy rock drifting through the void. It was an outlier in nearly every measurable way. A violation of patterns, a disruption of expectations, a reminder that the universe is still full of things we do not understand. This chapter explores that tension, the delicate boundary between conventional science and the extraordinary possibilities hovering just beyond it. It examines why 7 interstellar objects might appear at once, why one of them might seem unlike the rest, and how our expanding observational power is rewriting what we consider. Most importantly, it asks a question that once belonged only to fiction, but now presses against the edge of astrophysics. What if one of these visitors isn't entirely natural? And what if 3I Atlas is the first clue? For most of human history, the universe revealed itself sparingly. A comet every few years, a nova once in a century, a bright supernova maybe once in a millennium. Our ancestors thought the sky was calm, predictable, and almost empty. It wasn't. We were simply blind. The truth is that the universe has always been busy, filled with fragments of shattered worlds, ancient debris, drifting ice, and star-forged objects wandering between suns. But we never saw them, not because they weren't there, but because our tools were too weak to notice. That changed in the early decades of the 21st century. A quiet revolution began, one that would rewrite our understanding of the solar system's traffic. A revolution triggered not by a single telescope, but by an entire generation of machines designed to monitor the sky with relentless mechanical patience. The shift was so subtle that most of the world didn't notice, but astronomers did. They realized that the more we watched, the stranger the universe became. And by the time 2025 arrived, our new eyes were sharp enough to capture something almost unbelievable. A surge of interstellar visitors, arriving one after another, as if the darkness between the stars had begun to unclench its hands and release whatever it had been holding for billions of years. To understand why, we need to understand the revolution behind our seeing. The old way, human eyes, small telescopes, and chance. For centuries, discovering a comet required luck, a clear sky, a sleepless observer, a willingness to stare into darkness for hours. Even in the modern era, before automated surveys, the process was slow. Telescopes had narrow fields of view, and astronomers could only inspect one tiny patch of the sky at a time. Imagine trying to understand an entire ocean from a single cup of water. That was early astronomy. Most interstellar visitors passed through unnoticed, their tails faint, their duration short, their paths too steep for our limited instruments. We probably missed thousands, maybe millions, of objects that slipped through the inner solar system long before humans built their first wide-field survey. The turning point. Machines take over. Everything changed when we taught machines to watch the sky for us. Telescopes began scanning automatically, night after night, year after year, capturing thousands of images per hour and comparing them against each other pixel by pixel. Anything that moved, flickered, brightened, or dimmed was flagged instantly. Algorithms replaced human luck. Data pipelines replaced ink notebooks. And for the first time in history, we watched the universe with eyes that never tired. This was the beginning of the surveillance age of astronomy. But one machine would take this transformation to a level no one had seen before. The Vera C. Rubin Observatory, a new kind of vision. The Rubin Observatory wasn't built to find comets. It wasn't even designed specifically to find interstellar objects. It was built to do something grander, to capture the entire visible sky every few nights, with a camera so large it could image several full moons in a single shot. Its mission was to measure dark matter, track the evolution of galaxies, and detect the subtle flicker of unseen forces shaping the cosmos. But in accomplishing these tasks, it also became the most powerful hunter of transient objects ever created. Small things, fast things, dark things, unpredictable things. Objects that once slipped through the gaps of human attention now had nowhere to hide. The universe had always been chaotic. The Rubin Observatory simply revealed the chaos. And suddenly the solar system wasn't quiet anymore. The explosion of data as new surveys came online. Pan-STARRS, ZTF, Atlas, Catalina, DCAM. The number of discovered comets skyrocketed. Not because more comets appeared, but because our techniques improved so dramatically that the sky no longer felt like a distant mystery. We detected faint, inactive comets at enormous distances. We caught long-period comets years before they brightened. We identified tiny objects that would have been invisible 20 years earlier. And then came the unexpected. In 2017, we found Oumuamua. In 2019, Borisov. In the years that followed, more faint interstellar candidates appeared in archival datasets. It became clear that interstellar objects weren't extraordinary. Our blindness had been. The moment we opened our eyes, the universe revealed that it had always been sending visitors our way. But even with this new understanding, nothing prepared us for the wave of discoveries in 2025. 7 interstellar candidates in rapid succession. 7 anomalies in the data. 7 reminders that the cosmos is not as empty as we once believed. The surge wasn't a mystery of the universe. It was a consequence of our new vision. And yet, within this surge, one object still refused to be explained by technology alone. 31ATLAS. Improved observatories can explain why we see more visitors. They cannot explain why one visitor defies so many expectations. They cannot explain hollow signatures, or non-standard reflectivity, or erratic outgassing, or the possibility, however small, of controlled behavior near the sun. Better eyes reveal more of reality, but sometimes they reveal things that raise deeper questions. 31ATLAS is one of those questions. I eased the lantern open a little wider, letting the glow spill across the quiet room. Funny thing about light, it doesn't rush. It just waits for you to breathe. And as the pages turn, the world settles. The hum of the day drifts out of my head like sand sliding off a shoreline. All that's left is the soft warmth of the story, and the sense that something just beyond the dark is listening. The lantern keeper walks deeper into the valley now. The wind brushes past him, as if carrying memories that don't belong to him. He doesn't push them away. He lets them come. That's the thing about night journeys. If you walk long enough, the sky starts telling the truth. He lifts the lantern, and the mountains answer with a faint shimmer. Old paths waking up, footsteps forgotten by everyone except the stars. And I can't help thinking, maybe that's why these stories work on us. Maybe we're all just wandering through our own quiet valley, carrying a small light, hoping the world will whisper back. But the lantern keeper isn't afraid. He knows darkness only wins if you stop moving. So he keeps going. And so do we. The night deepens, the way it always does right before something important happens. Not louder, not brighter, just heavier, like the sky is holding its breath. The lantern keeper reaches a ridge where the air turns colder, sharper. The kind of cold that feels like a question pressed against your skin. He pauses, not because he's tired, but because the land ahead shifts subtly, like a thought you're not sure you should finish. The mountains seem to tilt toward him, as if inspecting the small figure with a stubborn little light. And for a moment he wonders if he's in the wrong place. That doubt hits fast, like a spark in the dark. But then the lantern hums. Not loudly, just enough to remind him that even a frail light can argue with the dark and win. So he steps forward. The ground changes beneath him. Stone gives way to a path etched with symbols, curves, spirals. lines that look like they've been waiting centuries to be noticed. He brushes his fingers over one, and the mark warms under his skin. Someone was here before him, someone who walked the same path with the same questions. The wind carries a whisper, not a voice, just a feeling. Go on. And he does. With every step, the lantern glow stretches farther than it should, touching parts of the valley the moon itself hasn't reached in ages. It feels less like a light and more like a memory waking up. And as he moves deeper in, he starts to sense it. Something ahead, something faint but unmistakable. A presence, watching, waiting. Not dangerous, not comforting either, just aware. The kind of awareness that tells you you're no longer walking alone. And somewhere inside me, reading this, I feel that quiet shift too, as if the story and the night and the room all lean in a little closer. The lantern keeper takes another step. The darkness blinks. The universe rarely offers moments that demand our full attention. Rarely does it align chance and circumstance in such a way that a single set of observations can redefine our understanding of cosmic history. Yet 2025, with its hypothetical surge of interstellar comets, presents exactly that. From the perspective of planetary science, this is unprecedented. Every comet that drifts through our solar system is a messenger from a distant world, a frozen fragment of material untouched for billions of years. In this extraordinary scenario, we are presented with not one, not two, but 7 interstellar travelers, each carrying the chemical fingerprint of an origin outside our solar system. The comparative study alone is staggering. Imagine analyzing frozen samples from multiple regions simultaneously. Fragments from the Oort cloud, from the scattered disk, from the interstellar void beyond the gravitational reach of our sun. Each sample, distinct in its isotopic ratios, in its mineralogy, in its organic complexity, opens a window into planetary formation processes far beyond Earth. It allows astronomers to answer questions that have long hovered at the edges of our understanding. How common are certain volatile compounds? How do planetary disks around other stars distribute ice and rock? Can we trace the chemical paths that lead from simple molecules to prebiotic compounds? And there is more. The sun, a seemingly constant beacon, becomes an active laboratory when multiple comets arrive concurrently. The solar wind, the radiation pressure, and the tidal forces that act on these comets are extreme. They shred the surfaces, evaporate volatile ices, and sculpt tails that stretch for millions of kilometers. Observing these interactions in real time provides a unique lens into solar physics. We can see how the sun sculpts matter, how it excites, transforms, and sometimes destroys. For once, we are not just passive observers of the cosmos. We are witnessing a direct experiment orchestrated by nature itself. And yet the scientific significance doesn't stop at physics. Organic molecules embedded in these icy bodies may carry the secrets of life's building blocks. Analyses of amino acids, sugars, and complex carbon chains within these comets could illuminate the chemical origins of life. We might begin to map the pathways by which life spreads across the galaxy, carried silently on icy interstellar vessels for billions of years. The implications are profound. Even if none of the objects are artificial, even if all behaviors can be explained by classical cometary physics, the opportunity is still historic. It is a chance to collect a multi-point data set of unmatched value, to observe evolution in real time, to test models of planetary formation, solar interaction, and organic chemistry against objects formed under conditions entirely alien to our sun. This is the rarity every astronomer dreams of, a cosmic event that can rewrite textbooks before the ink has dried. Segment 2 for the public. A spectacle not to miss. For the ordinary observer, the thought of 7 comets converging on our solar system is breathtaking. Even without advanced telescopes, the arrival of these objects promises a display unlike any in living memory. Bright tails, arcs of dust, the fleeting shimmer of ice sublimating in sunlight, these are phenomena meant to awe, to remind us of our place in a vast, active cosmos. Astronomy enthusiasts should prepare, telescopes aligned, cameras at the ready, eyes scanning the night sky for the slow, deliberate march of these celestial visitors. Amateurs and professionals alike can capture these moments, preserving them in images and memories alike. And for those without instruments, observatories around the world can provide live feeds, real-time tracking, and commentary. Every night becomes a lesson, every sighting a chance to marvel. This is more than a spectacle. It is an invitation, a reminder that the sky above us is not static, not predictable, not empty. It pulses with events that are rare, fleeting, and magnificent. We are reminded that we are spectators in a grand theater, a theater without walls, spanning billions of kilometers and untold centuries. Segment 3. Maintaining rationality and an open mind. Yet while the spectacle beckons, caution must guide our interpretations. Extraordinary claims require extraordinary evidence. Until solid proof emerges, the simplest explanation that these are natural objects, shaped by the physics of ice, rock, and gravity, remains the default. But caution does not imply closed-mindedness. The universe is vast beyond our comprehension. Phenomena may exist that challenge everything we think we know. Perhaps there are processes, forms of matter, or even traces of life that we are not yet capable of recognizing. Perhaps in the interplay of chance, physics, and cosmic time, there exist objects whose behavior defies the patterns we have cataloged. The potential comet surge of 2025, whether real or hypothetical, is exactly the kind of catalyst that drives science forward. It forces observation. It provokes measurement. It demands that we ask questions previously dismissed as speculation. And in doing so, it stretches the boundaries of what we consider possible. Segment 4, summarizing the cosmic lesson. The imagined events of 2025 combine rigorous science and speculative exploration. They draw on established knowledge, cometary physics, interstellar trajectories, the Oberth effect. Yet they also embrace the improbable, almost statistical impossibility that makes such a surge compelling. Whether these 7 comets represent the intricate handiwork of nature or the quiet, deliberate visit of extraterrestrial neighbors, the lesson remains profound. Humanity's understanding of the cosmos is nascent. Our night sky, long a symbol of constancy, is filled with surprises, mysteries, and moments of wonder. Every comet, every anomaly, every unexpected visitor is a reminder. The universe is alive with questions, and our journey toward answers has only just begun. While no official astronomical agency predicts a comet swarm of this scale in 2025, this scenario illustrates the union of science and imagination. It allows us to explore the what-ifs, to ask meaningful questions about the universe, about life, and about the limitations of our knowledge. Even as fiction, the scenario enriches our understanding of the scientific method, observation, hypothesis, and cautious interpretation. Above all, it reminds us that the night sky is more than a backdrop. It is a frontier. It is an invitation. And it is proof that the unknown still holds power, beauty, and awe. Each interstellar comet carries with it a story older than the Earth itself. Every grain of ice, every speck of dust, every trapped gas bubble is a relic of cosmic processes that took place far from the warmth of our sun. Studying these visitors offers the chance to compare planetary formation across multiple environments. In our own solar system, we have samples from meteorites, from asteroids, from comets, occasionally captured and returned by spacecraft. But all of these come from a single stellar neighborhood, the Sun's system. Interstellar objects, by contrast, are born elsewhere. They have formed under different stellar masses, in disks with different temperatures, metallicities, and dynamics. They have endured billions of years of interstellar travel, bombarded by cosmic rays, micrometeoroids, and the faint pressure of starlight. By examining 7 such comets arriving nearly simultaneously, scientists could construct a comparative framework unlike any before, not just observing differences in composition, but tracing the influence of environment on planetary formation. Some comets may be ice-rich, some rock-rich, some harbor rare elements that tell of formation around metal-poor stars. By mapping isotopic ratios of hydrogen, carbon, nitrogen, and oxygen, researchers can infer stellar histories and even galactic chemical evolution. This is the closest humanity will get to holding pieces of other worlds in our instruments. And with each analysis, our understanding of how planets form, evolve, and survive in different corners of the galaxy expands. It is a moment where interstellar exploration comes to us, carried silently through the void. Part 5, Segment 6, The Sun as a Laboratory. The Sun, often considered a constant, predictable star, becomes an active participant when these objects pass near perihelion. Imagine multiple comets approaching the inner solar system simultaneously. Solar radiation heats their surfaces unevenly, driving sublimation in unpredictable ways. Solar wind interacts with dust and gas tails, producing streams of charged particles. The comet's fragile nuclei may fracture under tidal stresses, creating ephemeral, complex systems of secondary fragments. For solar physicists, this is a natural experiment of unprecedented scale. Observing these interactions in real time allows measurements of solar wind density, magnetic field variations, and plasma interactions on scales impossible to reproduce in a laboratory. Every particle ejected, every tail disrupted, every spike in brightness is data. Data that speaks of the sun's influence and the resilience of small bodies under extreme conditions. It is the kind of opportunity that might occur once in several centuries, or even millennia. The timing of 2025, coinciding hypothetically with a solar activity peak, magnifies the value. Astronomers can witness not just the effects on one body, but the relative behavior of multiple comets subjected to identical solar conditions. Part 5, Segment 7, Tracing the Origins of Life. Perhaps the most tantalizing possibility lies in the comet's organic composition. Comets are often described as time capsules. Their ices may contain amino acids, simple sugars, and complex carbon-based molecules, all essential ingredients for prebiotic chemistry. Interstellar comets, having formed in environments beyond our solar system, could carry alternative chemistries. They could reveal pathways for the formation of complex molecules under conditions very different from those around the Sun. For astrobiologists, this is a once-in-a-lifetime chance to test whether the chemistry that leads to life is universal or highly contingent on local conditions. If molecules unique to these comets are detected, they could reshape our understanding of how life might spread through the galaxy. The idea of panspermia, that life's seeds travel across star systems via icy bodies, becomes not just theory, but a testable possibility. Even if the comets are lifeless, their chemical diversity may illuminate the vast potential for life-bearing environments elsewhere. Part 5, Segment 8, Engaging the Public. Scientific value aside, the spectacle itself cannot be overstated. Even for casual observers, the night sky of 2025 could be transformative. Multiple bright tails, shifting arcs, and cometary wakes illuminated against a clear sky. These are moments designed to inspire awe. Astronomers, amateur and professional, prepare their instruments. Cameras and telescopes poised to capture fleeting moments of cosmic choreography. Even those without access to telescopes can follow live streams, projections, and visualizations provided by global observatories. The public engagement aspect is crucial. Moments like this rekindle curiosity, excitement, and wonder. They remind us that science is not confined to labs, equations, or satellites. It is experienced with the senses, shared collectively, and cherished personally. Part 5, Segment 9, Rationality and Openness. And yet, even amid the spectacle and opportunity, caution is essential. Extraordinary claims require extraordinary evidence. Until solid, reproducible observations confirm anomalous behavior beyond known physics, natural explanations remain the baseline. But rationality does not demand closed-mindedness. The universe is vast, the conditions are extreme, and phenomena beyond our current comprehension almost certainly exist. The surge of 2025, real or hypothetical, represents a challenge to our assumptions. It asks us to prepare not just instruments, but our minds for phenomena that could stretch the boundaries of known science. Open-minded rigor, skepticism balanced with imagination and careful observation, these are the tools we bring. They allow us to capture not only data, but understanding. To capture the full value of such a rare celestial event, astronomers must coordinate like never before. Observatories around the world would need to synchronize schedules, combining optical, infrared, and radio observations to build a complete picture of each comet's structure and behavior. Telescopes like the Vera C. Rubin Observatory, already designed to scan the sky with unprecedented depth, would allow repeated imaging to track subtle changes in brightness and tail morphology. Spectroscopic instruments could analyze chemical composition in real time, detecting volatile ices, silicates, and organic molecules. Even small, ground-based telescopes could contribute, monitoring rotational rates, documenting fragmentations, and recording tail evolution. Every photon counts. Every observation adds a piece to the puzzle of how interstellar matter behaves under the influence of a star not its own. For a scientific community used to waiting decades for significant interstellar arrivals, the opportunity would feel like a once-in-a-lifetime alignment of cosmic fortune. Part 5, Segment 11, Engaging Citizen Scientists. The public can also play a role. Modern technology allows amateurs to contribute meaningful data. High-resolution cameras, backyard telescopes, and smartphone apps connected to global networks can track comet positions, measure brightness, and even capture transient crowdsourced observations could help verify anomalies, confirm trajectories, or detect small outbursts of activity. In this way, the event becomes not just a spectacle, but a collaborative scientific enterprise. The line between professional astronomer and citizen observer blurs as curiosity, preparation, and access combine to form a planetary-scale network of witnesses. Part V, Segment 12, Interpreting the Data, Science First. As observations accumulate, interpretation becomes critical. Each comet's brightness, trajectory, tail structure, and chemical composition must be compared against models of natural cometary behavior. Many phenomena that initially seem anomalous may have simple explanations: uneven sublimation, rotational instability, tidal stress, or gravitational perturbations. Rarity does not equal artificiality. The universe is vast, and statistical anomalies occur with regularity in unpredictable ways. Even events that seem coincidental may simply reflect the complex, chaotic dynamics of interstellar space. Nevertheless, scientists must remain open to the unexpected. Any deviation from well-modeled physics could indicate a process not yet understood, or in the realm of speculation, a sign of intentional design. The key is evidence, measured carefully, recorded meticulously, and interpreted rigorously. Part 5, Segment 13, Speculative Possibilities. Here, imagination intersects with scientific. Some propose the Zhu hypothesis, that extraterrestrial civilizations observe developing worlds without direct interference. Could these interstellar comets be vehicles of study? Could they carry sensors, probes, or even microbial payloads designed to seed or monitor other star systems? Others suggest panspermia, the natural distribution of life's building blocks via comets. In this framework, 2025's cometary surge could be a natural experiment, designed by nature, not intelligence, yet serving the same purpose, delivering chemical precursors of life across the. Even if these are natural comets, their synchronized arrival and observable behavior provide a rare window into processes that could otherwise remain purely theoretical. Science and imagination need not conflict. Both offer insights. Part 5, Segment 14, Philosophical Reflections. Finally, this hypothetical event reminds us of something profound. Our perspective is limited. We are infants in cosmic time, observing a universe that has existed for billions of years. Each comet is a messenger from that past, a frozen fragment of environments we may never fully visit. Moments like this force reflection, the interplay of chance, natural law, and possibility. The universe is vast, dynamic, and full of surprises. It challenges us to remain humble, curious, and ready to adapt our understanding. Whether the comets are purely natural, subtly artificial, or a combination of both, they inspire awe, inquiry, and philosophical wonder. They remind us that the universe is a stage larger than we can imagine, and that our role is to observe, interpret, and marvel. While the 2025 cometary surge offers immense scientific and observational value, safety must remain a priority. Though comets themselves are not directly threatening to Earth, their potential debris streams, dust trails, and interaction with the solar wind could pose minimal but measurable risks to satellites and spacecraft. Operators of high-orbit satellites, the International Space Station, and deep space probes would need to carefully monitor the trajectories of these interstellar objects. Predicting potential meteoroid streams allows for timely adjustments to spacecraft orientation and shielding measures. Additionally, ground-based observers should remember that the beauty of a celestial event does not eliminate the need for caution. Viewing directly with unfiltered optical instruments can harm vision, and navigating outdoor terrain at night can be dangerous without proper preparation. In this way, the comet surge becomes not only an intellectual opportunity, but also a lesson in practical preparedness, the delicate balance of wonder and responsibility. Part 5, Segment 16. Preparing the public for observation. For skywatchers, the year 2025 could be transformative. Amateur astronomers and casual observers alike are encouraged to follow observatory forecasts, align telescopes when possible, and track the positions of the comets across the night sky. Even simple tools like binoculars can reveal the faint glow of icy tails, while photography can document the changing structures over successive nights. Observing multiple comets simultaneously adds complexity. Some may brighten rapidly, others fade or fragment unexpectedly. A coordinated approach, sharing images, timing observations, and reporting unusual behavior ensures that the public engagement contributes meaningfully to the global dataset. The lesson here extends beyond astronomy. Engagement, curiosity, and preparedness are as important as the phenomena themselves. By fostering awareness and participation, humanity transforms from passive stargazer to active observer, shaping our collective understanding of the cosmos. Part 5, Segment 17, Anticipated Discoveries. The scientific payoff could be staggering. Comet brightness measurements could reveal sublimation rates previously unseen in interstellar objects. Spectroscopy might uncover novel organic molecules or unusual isotopic ratios, reshaping our understanding of chemical diversity across the galaxy. Fragmentation events could illustrate the structural limits of small, icy bodies formed far from any star, revealing the effects of billions of years in interstellar space. Each dataset contributes not just to cometary science, but to planetary formation theory, solar physics, and astrobiology. Even null results, if no unusual chemistry or behavior is found, are valuable, providing constraints on models and enhancing predictive capabilities for future interstellar objects. Part 5, Segment 18, Balancing Skepticism and Wonder. The duality of this scenario lies in the balance between skepticism and imagination. Science demands careful observation, reproducibility, and critical analysis. Every anomaly must first be measured against known physics and natural processes. Extraordinary interpretations, such as intelligent design or deliberate interstellar seeding, require evidence far beyond anomaly alone. Yet imagination fuels discovery. Considering alternative explanations, entertaining the possibility of unconventional phenomena, and asking what-if questions expands our conceptual framework. It is this balanced, rigorous methodology tempered with creative inquiry that allows humanity to make sense of rare, complex, and potentially paradigm-shifting events. Part 5, Segment 19, Philosophical and Cultural Reflections. Beyond data and observation, the cometary surge invites reflection on our place in the universe. We are witnesses to an event that may never recur in our lifetimes. These icy interstellar travelers are both familiar and alien, composed of the same fundamental elements as Earth, yet shaped in distant stellar nurseries. They remind us of the universality of matter and the uniqueness of circumstance. Cultural significance emerges naturally. Stories of comets as omens or harbingers, once dismissed as superstition, now resonate with scientific metaphor. The sky teaches humility. No matter how advanced our technology, the cosmos can still surprise us, evoke awe, and challenge assumptions. This interplay of observation, reflection, and imagination is the essence of human engagement with the universe. It is where science meets philosophy and where knowledge meets wonder. Part 5, Segment 20. Preparing for the unknown. Finally, the greatest lesson of a cometary surge lies in preparation for the unexpected always awaits in the cosmos. Comets may fragment, brightness may spike unpredictably, and anomalies may appear that defy models. Our response, careful, patient, curious, and adaptable, shapes what we learn and how we integrate it into human understanding. The year 2025, whether hypothetical or real, is an invitation to observe carefully, to think critically, and to remain open to discovery. It reminds us that science is not just a body of knowledge, but a way of seeing the universe, alert, humble, and ever curious. Every observation, every measurement, every night spent staring upward contributes to a larger story. A story in which humanity slowly, steadily, and beautifully discovers its place among the stars. The arrival of 7 interstellar comets in a single year is, statistically speaking, extraordinarily unlikely. From a purely probabilistic standpoint, most comets we detect originate within our own solar system. Interstellar objects, by contrast, are exceedingly rare. Only a handful have been confirmed since the first discovery of Oumuamua in 2017. To see several arrive within a narrow window challenges our assumptions about the distribution and frequency of such objects. Yet probability is not destiny. Over billions of years, rare events are inevitable, and clustering can occur purely by chance. This is the essence of a Poisson cluster, random events that appear grouped in time, though they are statistically independent. For scientists, this statistical understanding is critical. It tempers speculation and guides hypothesis formation. Even apparent anomalies can be framed within the expected variability of cosmic events, reminding us that rarity does not necessarily imply artificiality or intention. Part 5, Segment 22. preparing for the unexpected. The unpredictable nature of interstellar comets requires meticulous preparation. Observatories must be ready for sudden changes in brightness, fragmentation, or tail behavior. Space agencies need contingency plans for potential debris intersecting orbital paths. Amateurs must understand that observing interstellar objects is inherently dynamic. The sky may offer fleeting glimpses of phenomena that appear one night and vanish the next. Preparation is both technical and philosophical. Technically, it ensures data is captured efficiently, safely, and comprehensively. Philosophically, it cultivates patience and openness, recognizing that the universe does not conform to schedules, expectations, or human notions of neatness. This dual preparation, practical and cognitive, is the hallmark of rigorous science. Part 5, Segment 23, Hypothetical Scenarios. While natural explanations are most likely, speculative hypotheses are compelling. Artificial origins. Could some of these comets be disguised interstellar probes? Concealed by dust and ice, such objects could, in theory, carry instruments designed to monitor solar systems without detection. Their trajectories, perihelion behavior, and rotational dynamics would become critical data points for evaluating such possibilities. Panspermia in action. Interstellar comets could act as carriers of life's building blocks, spreading organic molecules across star systems. Observing the chemical composition of these bodies could test the universality of prebiotic chemistry. A coordinated cosmic event, the timing of multiple comet arrivals, could be coincidence, or could it reflect larger-scale dynamics in our galactic neighborhood? Gravitational nudges from passing stars, molecular clouds, or remnants of stellar explosions may occasionally funnel objects toward the inner solar system. Speculative scenarios, while improbable, help frame observational priorities. They encourage scientists to look for anomalies, prepare for surprises, and remain flexible in interpretation. Part 5, Segment 24. Integrating observations into human knowledge. Every observation contributes to an ever-growing tapestry of knowledge. Cometary brightness, tail morphology, fragmentation events, and chemical spectra all become data points in models of planetary formation, solar interaction, and astrobiology. Even null results, objects behaving exactly as expected, are valuable. They define baselines, constrain hypotheses, and sharpen predictions for future interstellar visitors. This integration of data transforms isolated events into cumulative understanding. Science advances not only by discovery, but by the careful construction of context, connecting each new observation to a broader framework of knowledge. Part 5, Segment 25, Philosophical Reflections on Rarity and Wonder. Rare cosmic events like this hypothetical comet surge provoke reflection on scale, chance, and perspective. We are but fleeting observers in the vast timeline of the cosmos. Events like these remind us that human experience is limited, but curiosity bridges that gap. There is a dual lesson. The universe is governed by law and chance. Statistical rarity does not imply meaning, yet it evokes awe. Natural processes can create moments that seem deliberate, orchestrated, or magical, reminding us that wonder is as much about perception as it is about reality. In this sense, observing interstellar comets is an act of philosophical engagement. It is a reminder that the cosmos is alive with possibility, that knowledge is provisional, and that imagination is a partner to empirical inquiry. The 2025 comet surge, hypothetical or real, carries consequences far beyond the immediate observations. Planetary formation models. Each interstellar comet provides insight into planetary formation under conditions entirely alien to our solar system. By analyzing isotopic ratios and chemical diversity, scientists can refine models of protoplanetary disk evolution, understanding how planets assemble across different stellar environments. Solar physics and space weather. Multiple comets interacting simultaneously with the solar wind offers a natural experiment in plasma dynamics. Insights from these interactions can inform models of solar flares, coronal mass ejections, and their potential impact on Earth's magnetosphere and technological infrastructure. Astrobiology and life's distribution. The presence of complex, organic molecules in these comets could shed light on the universality of life-building chemistry. Long-term studies could reveal patterns that indicate whether life is likely to arise independently in diverse planetary systems, or whether it propagates via interstellar delivery mechanisms like panspermia. Part 5, Segment 27. Educational Opportunities. Events like this provide a once-in-a-lifetime teaching moment. Schools, universities, and planetariums can use the cometary surge to inspire students, blending hands-on observation with lessons in physics, chemistry, and astronomy. Citizen science platforms could allow students to track comet trajectories, monitor brightness, or analyze spectral data, turning theoretical learning into practical experience. Documentaries, live streams, and interactive online platforms could engage a global audience, transforming curiosity into participation and encouraging a new generation to consider careers in STEAM fields. Part 5, Segment 28. Ethical Reflections. Speculative possibilities raise ethical questions as well. If interstellar objects were found to contain life, microbial or otherwise, what responsibilities would humanity have in observing, interacting, or collecting samples? Even in purely observational scenarios, we are reminded that our study of the universe carries consequences. Respect for natural processes, preservation of pristine cosmic environments, and careful consideration of our technological interventions are as important as scientific curiosity. Part 5, Segment 29. Cinematic narrative, engaging the audience. For a YouTube long-form narrative, this moment becomes a story. Imagine the night sky alive with multiple comets, tails stretching across constellations, illuminated by the sun. Viewers feel the scale, billions of kilometers of icy rock passing silently, relics of distant stars drifting past a tiny planet that has only just begun to understand them. Narration can combine awe with science, explain sublimation, tail formation, and interstellar origins, show simulations of perihelion passages, interactions with the solar wind, and potential fragmentations. Introduce the speculative what-ifs balanced with rational explanations, maintaining tension and wonder. Visuals, sound design, and pacing reinforce both comprehension and emotional engagement. allowing viewers to experience the event as both education and adventure. Part 5, Segment 30, Closing Reflections. Finally, we step back to consider the broader meaning. Whether the comets are purely natural or contain traces of unknown phenomena, they remind us of the vastness of the cosmos. Humanity is small in space and time, yet capable of observing, analyzing, and marveling at these events. The surge exemplifies the duality of science and imagination, grounded in evidence yet inspired by possibility. As we observe, calculate, and reflect, we participate in a dialogue with the universe itself. Every comet, every rare event, every anomaly challenges us to think bigger, to question assumptions, and to embrace the unknown with both rigor and wonder. In the end, 2025, real or imagined, is more than a year of comets. It is a reminder that the night sky is alive, the universe is dynamic, and our journey of discovery has only just begun. Throughout human history, comets have fascinated, alarmed, and inspired civilizations. From Halley's Comet to the Great Comet of 1811, humanity has observed these icy travelers as harbingers, storytellers, and natural phenomena. Historical records show that comets were interpreted as omens, influencing political, cultural, and religious decisions. Modern astronomy, of course, allows us to separate mythology from physics. Yet the emotional and cultural resonance remains. Observing 7 interstellar comets in 2025, a scenario unparalleled in recorded history, would echo the awe our ancestors felt, while providing scientific insight far beyond their imagination. By studying past comet events, scientists gain perspective. How observational techniques evolved, how predictions of brightness and trajectory improved, how interpretations shifted from superstition to rigorous scientific modeling. This historical lens enriches our narrative, reminding audiences that every observation today stands on the shoulders of centuries of curiosity and inquiry. Part 5, Segment 32, Analogies and Cosmic Scale. Analogies help audiences grasp the immense scale of interstellar comets. Consider each comet as a capsule, billions of years old, carrying the chemical fingerprints of distant stellar nurseries. The distances they travel, often tens of thousands of astronomical units, dwarf our solar system. Their journeys are epic, slow-motion odysseys, spanning light years, yet we witness them in real time as tiny points of light in the night sky. Analogies to human experience, a message in a bottle drifting across oceans, a relic traveling through time, can bridge understanding. This makes the narrative relatable without diminishing scientific accuracy, allowing viewers to emotionally engage while learning. Part 5, Segment 33, Building Cinematic Tension. In a YouTube long-form narrative, pacing and tension are crucial. Segments can alternate between scientific exposition, explaining sublimation, perihelion dynamics, tail formation, speculative wonder. What if these objects carry traces of life? Or could they be artificial? Observational suspense, showing simulations of sudden brightening, tail fragmentation, or unexpected trajectory shifts. By carefully layering these elements, viewers feel both the scale of the cosmos and the immediacy of observation. Narration should balance clarity and excitement, maintaining momentum while emphasizing the rarity and significance of the event. Part 5, Segment 34, Integrating Interdisciplinary Perspectives. The comet surge offers a convergence of disciplines: astrophysics, trajectories, brightness curves, solar interactions; astrochemistry, organic molecules, isotopic ratios, chemical diversity; astrobiology, implications for the universality of life, panspermia hypotheses; philosophy and culture, human perception, historical interpretations, existential reflection. This integration allows the narrative to appeal to a broad audience, blending rigorous science with curiosity-driven exploration. It emphasizes that understanding the cosmos is not the sole domain of physicists or astronomers. It is a shared human endeavor. Part 5, Segment 35, Observational Highlights to Emphasize. For viewers, highlighting visual and measurable phenomena creates a compelling story. Tail formation and dynamics. As comets approach perihelion, sublimation forms plasma and dust tails with distinct curvature and variability. Brightness variations. Sudden spikes or dips in luminosity can indicate outgassing events, rotation, or fragmentation. Fragmentation events. When a comet breaks apart, new mini-tails form, creating a mesmerizing visual effect. Color spectra. Cometary tails may display subtle color differences depending on composition, adding aesthetic and scientific value. Emphasizing these points with clear narration, animations, and live observations keeps the audience engaged while reinforcing educational content. When scientists propose that 3I Atlas might simply be a comet, one more frozen relic drifting into our solar system, it's easy for the public to feel disappointed. After all, it's the least cinematic option. It doesn't involve alien propulsion systems, doesn't hint at interstellar espionage, doesn't bring to mind sleek metallic crafts glinting under sunlight. But to scientists who study planets, chemistry, and long-distance cosmic travel, the boring hypothesis is actually the most scientifically electrifying. Why? Because if 3I Atlas is a standard comet, then it's not just any comet. It is a sample from a different solar system, hand-delivered across interstellar space. Comets in our solar system are chemical time capsules. They contain the leftover materials from the formation of the Sun and its planets, preserved in cold storage for 4.6 billion years. They hold pristine signatures of water formation, organic compounds, and heavy elements forged in ancient stellar furnaces. Now imagine having one of these time capsules, but from another star. That alone makes the ordinary comet hypothesis extraordinary. And perihelion, where 3I Atlas approaches the Sun closest, will turn the capsule's ingredients into natural fireworks. Sunlight will ignite the ices. Temperature will skyrocket. Gases will sublimate violently. Dust will be blasted into a luminous tail. In other words, the Sun becomes the microscope, and perihelion becomes the moment when the object reveals its true chemical alphabet. 2. The physics of sublimation, when ice turns to wind. To understand what scientists expect at perihelion, we have to examine the central process, sublimation. Unlike Earth, where water must melt into liquid before evaporating, cometary ices in deep space can transition straight from solid to gas when heated. It's an explosive, almost volcanic process on the microscopic scale. 3.1 ATLAS contains volatile ices such as carbon dioxide, CO, carbon monoxide, CO, possibly nitrogen or methane ices. Water ice, though likely less dominant due to its distant origin. At 1.36 astronomical units, the solar radiation it receives is more than 50% stronger than what Earth receives. That's a devastating amount of heat for delicate, interstellar frozen volatiles. Here's what scientists predict: CO sublimation storms. Carbon dioxide ice sublimates at only 80 to 90 K. 3.1 ATLA spent billions of years colder than that. By the time it reaches perihelion, coal will explode outward in violent jets, fountains of gas shooting from cracks on the nucleus surface. These jets act like tiny rocket thrusters, pushing dust, reshaping the coma, and altering the object's trajectory slightly. CO as a deep freeze signature. Carbon monoxide sublimates even at extreme cold, meaning its release can begin far from the sun. If 3IATLAS shows CO-dominated activity, that's a signature of a very cold birth environment, colder than anywhere in the early solar system. It would imply a star with a very low metallicity disk and extremely distant freeze-out zones. Water ice sublimation, the late fireworks. If 3I Atlas releases water vapor near perihelion, that means the object still holds interior reservoirs of water ice despite its interstellar journey. This single observation would revolutionize our understanding of thermal erosion during interstellar travel. Shielding by dust mantles, gas retention in small bodies, volatility survival over billions of years. Even a faint detection would carry enormous implications, predicting the light curve. How bright should it get? Every active comet has a light curve, a graph of brightness over time. And for 3IATLAS, the light curve is more than a measurement. It is a diagnostic tool. Think of it as the comet's ECG, its heartbeat. What a normal comet curve should look like. Astrophysicists model 3I Atlas using photometric behavior of hundreds of known comets. A standard interstellar comet with CO-rich composition should show gradual brightening starting months before perihelion. Steep surge in brightness as volatile ices erupt. Peak luminosity near the closest approach to the sun. Sharp decline as it moves outward and jets shut down. The exact slope of these rises and falls provides clues to nucleus size, volatile abundance, dust production rate, surface activity patterns, rotational behavior. If 3I Atlas matches these models, the standard comet hypothesis strengthens. If it deviates dramatically, particularly if brightness changes do not correspond to predicted thermal input, then scientists must investigate deeper. Volatility fingerprints. Each volatile has a different response to heat. CO equals early strong surge. HO equals late close-in surge. CO equals slow, steady, persistent release. Exotic ices equals unpredictable spikes. By analyzing how brightness changes minute to minute near perihelion, scientists can determine which ices dominate. Essentially, the light curve becomes a chemical signature written in photons. 4. The coma, a chemical atmosphere in motion. The coma, the cloud of gas and dust surrounding the nucleus, acts like an expanding atmosphere. Its shape, density, color, spectral fingerprints all reveal clues about the nucleus composition. Co-dominated coma. A CO-rich coma suggests formation extremely far from a star, low temperatures, a protoplanetary disk rich in carbon compounds, minimal heating events after formation. This implies 3I Atlas is a messenger from a frigid environment our solar system could never produce, an alien Kuiper belt, colder than anything we know. Dust composition. The dust blown off with the gases carries deeper secrets. Silicate grains reveal disk temperature. Organic molecules hint at chemistry pathways. Metallic dust grains reveal the star's metallicity. Isotopic ratios reveal stellar ancestry. Each grain is a souvenir from another solar system. A single dust spectrum can rewrite planetary formation theories. 5. Why a natural comet from another star is historic. It's tempting to think, so what? It's just frozen stuff from far away. But that's like saying a meteorite from Mars is just a rock. In cosmic terms, materials formed around other stars are unbelievably precious. 3.1 ITLAS is a free sample of another star's chemistry, a relic from another planetary nursery, untouched since the birth of a foreign solar system, older than human civilization, older than the Earth itself, perhaps older than the Sun. This makes it a cosmic fossil, a window into exoplanet formation. For decades, scientists have studied exoplanets indirectly through transit dips, radial velocity wobbles, or faint thermal signatures. But to hold actual material from another planetary system is something else entirely. From 3I to LAS, scientists can infer disk temperature gradients, chemical abundances, stellar metallicity, organic chemistry pathways, water formation processes, freeze-out radii, dust enrichment cycles, irradiation history. One comet can inform the physics of millions of planetary systems. 6. Why Perihelion is the moment of revelation. The sun is not just a source of light, it is a destructive laboratory. As 3I Atlas approaches perihelion, surface temperature skyrockets, dormant ices detonate outward, jets pierce the coma. The dust mantle fractures, rotation may shift, outgassing turquoise alter its path, exotic volatiles vaporize. The coma blossoms into full display. Every one of these changes is observable. Every one answers a scientific question. Perihelion is the truth serum. If the object behaves as models predict, Gibbs' standard comet hypothesis gains enormous weight. If not, Gibbs the door opens to rare physics or to technology. 7. Even if it's normal, it still changes everything. This hypothesis natural comet may sound less dramatic, but from a scientific perspective, it is the most revolutionary. A natural interstellar comet is a messenger from another star, a relic from beyond the sun's gravitational influence, the only physical sample of other planetary systems humanity can study, a critical calibration point linking planetary formation theories, a chemical fingerprint of distant stellar nurseries, an object shaped by billions of years of interstellar erosion. And it requires no aliens, no propulsion, no technology. Nature on its own is capable of producing astonishing complexity. Even the simplest explanation here still rewrites textbooks. 1. The hypothesis that refuses to die. For decades, astronomers have worked under a professional code. Extraordinary claims require extraordinary evidence. But when 3I Atlas arrived interstellar, active, puzzling, and heading toward the sun, the old debate resurfaced like a half-buried fossil. Could it be a natural object? Yes. Is that the simplest hypothesis? Absolutely. But is it scientifically illegal to consider another option? Not at all. Avi Loeb and a small but vocal minority argue that interstellar objects could, in principle, include non-natural artifacts. Not because they are artificial, but because the universe is old, vast, and full of technological potential. The alien probe hypothesis is not a claim. It is a question. And perihelion, the moment when 3I-ATLAS skims past the sun, is the best time to answer it. But to understand why, we must first explore the underlying engineering. This isn't science fiction. This is straight orbital mechanics. 2. The Oberth effect. Rocket science's divine cheat code. If aliens wanted to accelerate, decelerate, or redirect a probe, they would do it near. Why? Because of a quirk of physics called the Oberth effect. Think of it this way. An everyday analogy. Imagine you're sliding down a hill on a sled. At the bottom, you're going the fastest. If you kick your legs and push while you're moving slowly at the top, you barely gain speed. But if you push at the bottom, when you're already zooming, you rocket forward. Same energy, different result. Because speed amplifies thrust. A spacecraft works the same way. The physics version, simplified. When an engine burns fuel at high velocity, the kinetic energy gained per unit fuel is maximized. At perihelion closest to the Sun 3I Atlas will be, at its highest velocity, experiencing max gravitational acceleration, in the perfect location for maneuvers. A small burn here equals a huge trajectory change. If 3I Atlas were a probe, perihelion is where it would act. Not before, not after, here. This is why Loeb calls perihelion the acid test. If the object sharply deviates from predicted orbit, changes spin unexpectedly, splits in unnatural ways, maintains stability against thermal stress, performs impulse-like accelerations, then the alien probe hypothesis must be considered seriously, not accepted blindly, but treated as a legitimate scientific question. 3. Potential maneuvers a probe might attempt. If 3I Atlas were technological, perihelion offers 3 strategic opportunities. Let's explore them one by one. A. Maneuver 1, deceleration, letting the sun capture it. This is the boldest scenario. If the object fires retrograde opposite its direction of motion, even a small amount of thrust could slow it enough for the sun to gravitationally capture it. It would no longer be an interstellar traveler. It would become a permanent resident of the solar system, a stowaway planetesimal. What would be the purpose? Establishing a long-term monitoring station, creating a solar-powered outpost, studying Earth from afar, using the sun's vantage point for data gathering, hiding inside the enormous glare that blinds most astronomical instruments. To achieve capture, only tens of meters per second of delta V might be needed, tiny for a spacecraft. A natural comet cannot produce such controlled retrograde thrust. Its jets produce chaotic, random forces. A deliberate, directional slowdown would be unmistakable. B. Maneuver 2. Acceleration slingshot toward the inner planets. Alternatively, the object could accelerate with its motion, using the Oberth boost to fling itself toward Earth, Mars, Venus, the asteroid belt. Each trajectory has engineering value. Toward Earth gives close flyby, data collection, magnetosphere sampling, radio silence detection, atmospheric spectroscopy. Toward Mars or Venus gives broad survey of planetary atmospheres and geology. Toward the inner asteroid belt gives resource scanning, mineral sampling, mapping gravitational anomalies. If 3I Atlas shows an unnatural increase in heliocentric velocity after perihelion, it would be one of the strongest possible signs of engineered propulsion. Comets can accelerate, but only through sublimation and always in predictable thermally driven directions. Not sideways, not precisely aligned, not synchronized with peak velocity. C. Maneuver 3. Redirection, a sharp turn toward the outer planets. This option is subtle but powerful. Instead of joining the inner solar system, the probe could use the Sun to sling itself toward Jupiter, Saturn, the Kuiper Belt, the heliopause, interstellar space if it's just passing through. Why visit the outer planets? Because Jupiter is the solar system's central gravitational hub, the ultimate slingshot engine. A craft that reaches Jupiter can redirect anywhere, accelerate rapidly, hide in the radio-noisy environment, tap gravitational assist to leave the system entirely. If 3I Atlas executes an unnaturally sharp turn after perihelion, especially toward Jupiter, that would be a red flag. Natural bodies follow smooth, predictable curves. Artificial probes follow intentions. 4. The dandelion seed hypothesis, releasing microprobes. This is one of the more exotic yet physically plausible ideas. Some engineers propose that extraterrestrial civilizations may not send a single large probe, but thousands of microscopic ones, lighter, stealthier, harder to detect. Imagine a dandelion head and a gust of wind. Tiny seeds released, drifting silently, spreading over a vast area, nearly impossible to track individually. If 3I-ATLAS were a carrier probe, perihelion would be the perfect moment to release microdrones. The sun's glare provides visual hiding. Solar radiation pressure can spread them. Their tiny size makes radar detection nearly impossible. Their diverse trajectories allow wide solar system coverage. These microprobes gram scale or even milligram scale could analyze solar wind, sample interplanetary dust, listen for radio emissions, map gravitational fields, approach planets silently. Would we see them? Probably not. But we would notice if 3I-ATLAS's mass distribution suddenly changed, impacting its motion in subtle but detectable ways. A natural comet cannot eject mass with engineered precision. 5. What would alien engineering look like? If 3I Atlas were artificial, its observable signatures might include A. Non-thermal acceleration. Comet jets must align with sunlight-driven heating. Thrusters do not. If acceleration occurs from the unlit side or contradicts heating models, gives red flag. B. Structural integrity at impossible temperatures. Interstellar comets are fragile snowballs. Spacecraft are not. If the object passes perihelion without measurable fragmentation, gives suspicious. C. Unusual rotation patterns. A spacecraft corrects spin intentionally. A comet does not. Sudden stabilization or regularization of spin gives unnatural. D. Radar reflectivity anomalies. Metal reflects radar sharply. Dusty ice does not. If its radar signature resembles metallic density, gives highly unusual. E. Shape retention. If it maintains a smooth, geometric, or symmetric outline after heating, gives abnormal for natural bodies. Science doesn't jump to conclusions, but these signals would force reconsideration. 6. What the scientific community actually thinks. Contrary to public perception, most scientists are not hostile to the alien hypothesis. They're cautious. Here's the breakdown. Supporters, open-minded scientists. They argue the universe is old enough for advanced civilizations. Technological artifacts could drift into our solar system. Considering artificial origin is rational, not sensational. Dismissing possibilities without evidence is unscientific. Interstellar visitors are rare and deserve full-spectrum analysis. Avi Loeb is their leading voice. He argues not for belief, but for permission to ask the question. Skeptics, traditional astrophysicists. They argue natural explanations must be exhausted before exotic ones. Comets are known to behave unpredictably. No evidence currently requires artificial interpretation. Extraordinary claims must be backed by data, not curiosity. They don't oppose the idea of alien technology. They oppose premature conclusions. Neutral researchers, the silent majority. They simply want more data. Most astronomers fall here, practical, diligent, and fully aware that the cosmos is capable of surprises. 7. Why the alien probe hypothesis matters, even if it's wrong. Some people ask, why bother with such an unlikely idea? Because scientific progress requires openness, not dogma. Considering artificial origin forces high-resolution observation, inspires more rigorous modeling, encourages better instruments, trains scientists to avoid bias, expands the conceptual space of planetary science, brings public attention to astronomy. May one day be correct. The point is not to prove aliens exist. The point is to study 3I Atlas with the full creativity of science, not the cautiousness of bureaucracy. Whether natural or artificial, every possibility teaches us something about the universe and about ourselves. 8. If it is a probe, what happens next? Hypothetically, does it contact us? Probably not. Does it slow down for inspection? Unlikely. Does it reveal itself? Even less likely. Does it simply pass through, gathering data silently? Very possible. If alien technology exists, it may operate like our own deep space probes, quiet, passive, patient, observational. We don't announce Voyager 1 to every star we pass. We just let it drift and listen. If a civilization is millions of years older, its probes might act just as quietly. Either way, Perihelion is the moment of truth. If there is one idea within the extraterrestrial probe hypothesis that both fascinates engineers and unnerves astronomers, it is this. 3-1 Atlas might not need to perform any dramatic maneuver at all. It could simply shed smaller probes quietly, invisibly, and irreversibly while the sun's glare blinds every telescope pointed its way. Why near the sun? Because physics becomes the perfect accomplice. When an object approaches perihelion, three things happen simultaneously. Solar glare saturates detectors. Telescopes lose contrast. Even the most advanced coronagraphs struggle. A faint metallic shard or a mirror-coated wafer probe is effectively invisible. Solar wind becomes a natural dispersal mechanism. If you release lightweight chips, say, gram-scale wafers, they behave like pollen in a storm. They drift, accelerate, scatter. Tracking them becomes nearly impossible. Any anomalies are masked by expected comet activity. If 3I were a normal comet, it would release gas jets, dust plumes, and fragments. Hiding small probes inside that chaos? Perfect cover. This is the logic behind what some have dramatically called the dandelion scenario. The dandelion scenario, a step-by-step breakdown. Picture 3 IATLA not as a monolithic craft, but as a carrier, a vehicle, whose true function is to scatter seeds. Seeds so small we barely notice them. Step 1. Heating phase. As 3I plunges inward, its surface layers natural or engineered heat rapidly. A cleverly designed composite shell could soften or destabilize at a predictable temperature, triggering release events. Step 2. Passive dispersion. The probes might have high reflectivity, thin film sails, centimeter-scale surfaces, gram or sub-gram. Such devices would be solar sail-assisted micro-explorers capable of drifting into the inner system with almost no energy expenditure. Step 3. Data collection. What would they measure? Solar wind chemistry, magnetic fields, asteroid compositions, atmospheric escape rates from terrestrial planets, technological signatures if intelligence is truly the goal, all while remaining effectively unrecoverable unless you knew where to look. Step 4. Long-term trajectories. The lumpiness has consequences. Gravity behaves differently in voids versus filaments. Time flows differently. Space expands at different rates. These differences are small but measurable. Accumulated over billions of years across billions of light years, they become significant. Some cosmologists began suggesting that the universe's apparent acceleration might actually be a side effect of this lumpiness. What if we're not properly accounting for how structure affects our measurements? What if dark energy is just an artifact of using oversimplified equations? This debate continues today. However, one thing is certain. The discovery of cosmic voids forced astronomers to confront an uncomfortable truth. The universe they thought they understood was far more complex than their models suggested. The smooth cosmic soup was a myth. Reality is messier, stranger, and far more interesting. But where did this structure come from? The cosmic web. The largest pattern in nature is invisible to the naked eye. You need telescopes. You need computers. You need millions of galaxy measurements processed through sophisticated algorithms. When you finally see it, the pattern takes your breath away. Scientists call it the cosmic web. Imagine a spider's web stretching across cosmic distances. But instead of silk threads, the strands are made of galaxies. Instead of empty air between the threads, you find voids. This structure fills the entire observable universe. It's everywhere. It's everything. The web has four main components. First, the voids. These are the bubbles, the empty regions where almost no galaxies exist. They range from 20 million to hundreds of millions of light years across. They occupy most of the universe's volume. 80% of space consists of voids. Second, the walls. These are sheet-like structures where galaxies cluster in two-dimensional surfaces. Imagine a soap bubble's surface. The walls of the cosmic web resemble these surfaces, except they're made of galaxies instead of soap molecules. The walls contain the typical cosmic density of matter. They're neither particularly empty nor particularly dense. Third, the filaments. These are the one-dimensional structures where walls intersect. Picture the edges where two soap bubbles meet. Filaments stretch for tens or hundreds of millions of light years. They contain higher concentrations of galaxies than the walls. Matter drains along filaments like water flowing through pipes. Fourth, the clusters. These are the nodes, the points where multiple filaments intersect. Clusters represent the densest regions of the universe. Thousands of galaxies packed together, bound by their mutual gravity. Clusters form at the junctions where walls and filaments meet, like knots in a net. This hierarchy exists because of gravity. Matter flows from low-density regions toward high-density regions. The voids empty out as their sparse matter gets pulled toward the denser areas. The walls collect this matter. The walls then drain along filaments. The filaments feed into clusters. The process happens slowly over billions of years. However, it happens relentlessly. The voids grow emptier. The filaments grow denser. The clusters grow more massive. The cosmic web evolves, with matter constantly redistributing itself. Our own galaxy, the Milky Way, sits on a filament. We're not in a void, thankfully. We're also not in a major cluster. We occupy a relatively average position in an average filament. Our location gives us a decent view of the cosmic web around us. We can see nearby voids. We can trace filaments stretching into the distance. We can observe clusters both near and far. The cosmic web's geometry determines the future of galaxies. Galaxies and voids evolve differently from galaxies and clusters. Void galaxies live in peace, undisturbed by neighbors. Cluster galaxies experience constant harassment, colliding and merging and having their gas stripped away by hot intergalactic plasma. The web also determines the distribution of matter and energy in the universe. Voids contain little ordinary matter, but dominate in volume. Clusters contain concentrated matter, but occupy tiny volumes. The walls and filaments hold the majority of ordinary matter, spread across intermediate volumes. Computer simulations can recreate the cosmic web's formation. start with a nearly uniform distribution of matter shortly after the Big Bang. Add tiny quantum fluctuations that create small density variations. Let gravity work for 13.8 billion years. The result looks remarkably like what we observe: walls, filaments, clusters, and voids. The cosmic web is not random. It's the inevitable result of gravity acting on an expanding universe with slight initial imperfections. It's beautiful, it's intricate, and it's all connected. However, what's most striking is what dominates the web. By volume, most of the universe is nothing. This statement sounds paradoxical. How can nothing be most of anything? However, when we measure the universe's volume and calculate how that volume divides between dense regions and empty regions, the math is clear. Voids occupy approximately 80% of the cosmos. 80%. Let that sink in. 4/5 of all space contains almost no matter, no stars, no planets, no gas clouds. Just vast, dark emptiness, separated by thin walls and threads of galaxies. This ratio has profound implications. We live in the minority of the universe. Our galaxy exists in a dense region, relatively speaking. We're on a filament surrounded by other filaments and walls. From our perspective, the universe looks crowded with galaxies. We can see thousands of them with large telescopes, billions with the most powerful instruments. However, our view is biased. We see the bright structures because that's where we live. We're like a fish in the ocean who assumes the entire world is water. The fish never experiences dry land, never sees the atmosphere, never knows that most of Earth's surface is not ocean. Similarly, we experience the cosmic web's dense parts. The voids remain mostly hidden, visible only through careful mapping and statistical analysis. If you could randomly place yourself anywhere in the universe, you would have an 80% chance of appearing in a void. You would look around and see almost nothing, a handful of faint, distant galaxies scattered across the sky. Everything else would be darkness. This probability reveals something important about cosmic structure. The universe is defined more by its absences than its presences. The places where galaxies don't exist occupy more space than the places where they do. Think about that from an information perspective. If you wanted to describe the universe's structure, you could list every galaxy's position. However, it might be more efficient to list every void's position and size. There are fewer voids than galaxies, but they take up more space. The voids are the primary structures. The galaxies just outline them. The 80% figure also matters for understanding the universe's evolution. Voids are not static. They grow as the universe expands. Voids expand faster than the average expansion rate. This happens because voids contain less matter, which means less gravity holding things together. With less gravitational resistance, the expansion proceeds more rapidly. Meanwhile, dense regions expand slower than average. Gravity in clusters and filaments partially counteracts the cosmic expansion. Clusters might not expand at all internally. Their gravity is strong enough to hold them together against the expansion. This differential expansion means the 80% figure is increasing. Voids occupy a larger fraction of the universe's volume today than they did 1 billion years ago. 1 billion years from now, they will occupy an even larger fraction. The universe is becoming more empty with time. Currently, if you could swim through the deepest parts of voids, you might encounter a single hydrogen atom in a space the size of a football field. That's the density. One atom per several thousand cubic feet. In denser parts of voids, you might find a few more atoms. In the absolute deepest regions, even that sparse matter vanishes. For comparison, the interstellar space between stars in our galaxy contains about 1 atom per cubic inch. That's already a vacuum far better than anything we can create in laboratories on Earth. The voids are 1,000,000 times emptier than that. Some regions within voids are so empty that even dark matter thins out to near nothingness. These are the lowest density regions in the entire universe. Nothing approaches their emptiness. Yet, despite being 80% of space, voids remained largely ignored by astronomers until recently. Scientists focused on galaxies and clusters where the action happens, where stars form and die, where black holes devour matter and release energy. The void seemed boring, just empty space, nothing to see, nothing to study. That assessment was wrong. The first whispers. The story of cosmic voids begins at the very beginning. Not the beginning of voids themselves, but the beginning of everything. The Big Bang, 13.8 billion years ago. In the first fraction of a second after the Big Bang, the universe was smaller than an atom. It contained all the energy and matter that would eventually form every star, every galaxy, every planet. Everything was compressed into a space so tiny that quantum mechanics ruled absolutely. Quantum mechanics is weird. At quantum scales, nothing stays perfectly still. Nothing remains perfectly uniform. The laws of quantum physics demand uncertainty, fluctuation, randomness. These fluctuations are incredibly tiny. They occur at scales billions of times smaller than an atom. However, they exist. They must exist. The mathematics of quantum field theory requires them. These quantum fluctuations created tiny variations in the density of energy in the early universe. Some regions had slightly more energy, some had slightly less. The differences were incredibly small. We're talking about variations of 1 part in 100,000. Then the universe inflated. In the first fraction of a second, space itself expanded exponentially. In less time than it takes light to cross the diameter of a proton, the universe grew from subatomic size to roughly the size of a grapefruit. This period is called cosmic inflation. Inflation had a profound effect on those tiny quantum fluctuations. It stretched them. It amplified them. Fluctuations that started at quantum scales got blown up to macroscopic scales, then to astronomical scales, then to cosmic scales. By the time inflation ended, these quantum whispers had become cosmic shouts. Regions with slightly higher density were now millions of light years across. Regions with slightly lower density were equally massive. However, the variations remained small, about 1 part in 100,000 still. That was enough. Gravity then took over. Over the next hundreds of millions of years, regions with slightly higher density attracted matter from their surroundings. This made them denser still, which increased their gravitational pull, which attracted more matter. A positive feedback loop. Meanwhile, regions with slightly lower density lost matter to their denser neighbors. This made them even less dense, which weakened their gravity. which made it easier for surrounding dense regions to pull away remaining matter. Another feedback loop, but running in reverse. The rich got richer, the poor got poorer. Over hundreds of millions of years and billions of years, these tiny initial fluctuations grew into the cosmic web we see today. The overdense regions became clusters and filaments. The underdense regions became voids. Computer simulations can track this process in detail. Start with a nearly uniform distribution of dark matter and normal matter. Add the tiny fluctuations derived from quantum mechanics. Let gravity operate according to Einstein's equations and watch what happens. The simulation produces walls, filaments, clusters, and voids. The results match observations remarkably well. The voids formed first. This might seem counterintuitive. You might think dense structures would form first. However, remember that voids are defined by the absence of dense structures. As soon as matter started flowing out of underdense regions into overdense regions, voids began forming. Early voids were smaller. Over time, they merged. Two neighboring voids might have a thin wall of galaxies between them. That wall contained matter, but it was spread thin. Eventually, matter in the wall got pulled away by denser regions beyond the voids. The wall thinned and vanished. The two voids merged into one larger void.